Okay, let's start. So in the previous 6 lectures, we talked about this topological order, microscopic and macroscopic theory, and also this holographic view of symmetry. So today we try to discuss the application of all this formalism. Actually, all this formalism was developed just for those physical applications. And so first, let's just consider generic, the ordinary Ginzburg-Landau theory. So according to Ginzburg-Landau theory, the different symmetry breaking phase is classified by a group subgroup structure. So the group GH is a symmetry for the Hamiltonian, and the G phi is a unbroken symmetry of the ground state. So so this pair of group describe symmetry breaking phase. So that's how we label different symmetry breaking phase. Okay. Then we suddenly have the order parameter, which is transformed non-trivially under this symmetry transformation, and their average gave rise to an order parameter. The zero, non-zero describe this phase transition. Okay. So according to Ginzburg-Landau theory, at least what we believe is that the continuous transition can happen only between pair of groups G1, G2. If this if G1 is a subgroup of G2 or G2 subgroup of G1, the G1, G2 is an unbroken symmetry group. Okay. Okay, so this is just a standard understanding, but actually it's pretty tricky. So when we say, when you have a group subgroup structure, we think, yeah, the continuous transition is allowed. But somehow, at least for me, there's an impression that this continuous transition is a generic. So it's just ordinary, it's a so-called stable continuous transition with only one relevant operator. But actually, in general, this is not true. I think for Ginzburg-Landau theory, if you really been careful, the continuous transition is allowed, but the critical point may have many relevant operator, so may not be a stable one. Okay, so so we have this 4 symmetry breaking phase for this Z3 symmetry. Basically, we have to have 4 subgroups. Z1 is trivial, and Z2, Z3, and S3. Okay, so so in fact, this 4 symmetry breaking phase correspond to 4 gap phase of matter. Okay, and in general, for other group, we could have SPT states. For S3 group, there happen to be no SPT states in 1 dimension. And so, but for other group, in addition to symmetry breaking phase, we also have other SPT states. So there's a more structure, but here we only have 4 phases. Okay. So to really describe these 2 phases quantitatively, we introduce 2 order parameter. One order parameter is this it's like parity order parameter. So there's phi changing sign under this parity action. But under this cyclic permutation of 3 objects, this phi, little phi don't change sign. And there's 2D representation. That's a 1D representation. There's a 2D representation is a big phi. So under parity, the big phi 1, phi 2 get changed. And under the cyclic permutation, they just change it by a phase. So then we can use this 2 order parameter to construct a generic Ginzburg-Landau theory. It's rather complicated. The reason is following. If you have a simple one, actually there's an actual symmetries. So we add all these actual terms, make sure the symmetry of this theory is just S3, not bigger. Yeah. And so it's more complicated. But essentially, we have two terms. This U term and the V term. You can see the U and the V are quadratic, which control which order parameter want to be non-zero or which order parameter want to be 0. Okay. Then here, just taking this alpha beta gamma equal to 1, and the quadratic term just also equal to 1 for some convenience, and then we just get this this UV. This is really UV phase diagram. Okay. So there's so let's to orient it. So let's look at this line. This line. This top here. The top here is really correspond to this graph. So on the right, both are automatically to 0, and to the left, one order parameter, this big phi became non-zero, which break S3 down to Z2. Okay. And actually, this transition is the first order. It's not very obvious here, but it is first order. There's a jump here, finite jump. And so it's a first order really because the symmetry allow cubic term. This cubic term is allowed by symmetry. So that's the trouble. So that's one thing that the Ginsburg theory don't always guarantee the continuous transition, even when we have group subgroup relation. If there's cubic term, then you don't have this. You may have the first order transition. Okay. And similarly, down here, that's the question. This part. In this part, the little phi always non-zero. This brown line means the little phi always non-zero, which break S3 down to Z3 symmetry. So the big symmetry Z3. And then again, we have first order transition. The big phi from 0 to non-zero, we go from Z3 to nothing, no symmetry. That's also first order transition. Then in the middle line, if you cross this middle line here, so we have more complicated transition. And here we have first order transition. You can see that the big phi jump to non-zero, and the little phi go from non-zero back to 0. So there's a first order transition here. We'll go further, then we have a second order transition. This little phi from 0 to non-zero. So a second order transition. So that is basically the phase diagram. The lesson is that actually although we have a lot of group subgroup relation, the Ginsburg theories predict that many transitions are first order. We don't have a second order transition. Okay. And then you may ask, what really happened? So do we think there is no stable continuous transition between S3 and Z2 phase? So that's a question. According to the Ginsburg theory, the answer is no. We don't have such a transition because of cubic term. But in real system, when you do this real quantum one-dimensional system, we do have this transition. This transition is called a pulse model. The pulse model indeed have a continuous phase transition. And so this from S3 to Z2 transition is a continuous, not first order as predict by Ginsburg theory. So here just say the Ginsburg theory gives us some nice way to understand the phase diagram, but also kind of misleading, a lot of misleading results at the point. And to really see this, so let's consider a two-dimensional statistical model. So instead of do 1+1 dimensional quantum model, we do two-dimensional statistical model. Try to reproduce this phase diagram, basically, all the phase. The standard picture is just a pulse model. So pulse model just have this vector, but the vector won't have 3 directions. You know, this 120 degrees separate. There's 3 directions, so there's Z3 symmetry. So therefore, we can consider a statistical model where on the 2-dimensional square lattice, the neighboring interaction is such that when the neighboring vector are the same, the energy is low, is different, the energy is high. Okay. So then we get a transition from disorder phase to ferromagnetic phase. Just a one rotor, one Z3 rotor, just this part. And if you do this 1Z3 rotor, clearly that at high temperature we have disordered phase. The rotor just go over direction. At low temperature, rotor become ferromagnets, just all point in the same direction. And this is standard pulse model, and this pulse model have continuous transition. But this transition is not go from S3 to Z1, although it's ferromagnetic. When rotor get a point in one direction, it have a remaining Z2 symmetry. The reflection symmetry is not broken. Okay. So we have trouble actually. In the pulse model, we couldn't recover all 4 phases. We only have 2 phases in the pulse model, and only see 1 transition. We couldn't study other transition. Okay. So Well, so we have to build a more complex model. So actually, it's quite a trial to see which model can produce all the 4 phases. We come up with the model. Maybe maybe they're simpler model, but at least this model works. Okay. And in this model, it's a double rotor. We have two Z3 rotor. Okay. So one is given by theta and not given by phi. The reason we get 2 Z3 rotor is that we want to have this chirality. From theta to phi, whether we go to the right or go to the left. So the relative position between theta and phi give us chirality, and that is another important symmetry. Okay. And this S is an Ising variable, which is basically coupled to tell us the chirality, whether theta go to phi, from theta to phi is go to right or go to left. So basically that's this coupling. So this theta minus phi is a plus or minus coupled to this S Ising order parameter. So that's basically describe whether chirality is broken or not broken, in addition to whether rotor direction is broken or not broken. And so this is a trick, so that with this trick, with this model would have all 4 phases. And then we can start using this model to study how different phase, what their transition. Okay, again, look at the mean field theory. We have a model with S3 symmetry. There's a 4 phase with a full symmetry, no symmetry breaking. The S3 break down to Z2 symmetry. S3 break down to Z3 symmetry. S3 break down to Z1 symmetry. And then with for Ginsburg theory, we have this phase diagram. And for this model, we have this phase diagram depending on parameter. Okay. Again, this parameter I changing this J1, J2. I'm only changing J1, J2. So J1 tell us whether this rotor is ordered, not ordered. J2 control whether this chirality is ordered, not ordered, whether chiral symmetry is broken, not broken. So this is basically this J1, J2. And then this other parameter is equal to 1 or equal to this -1 and 1. So there's other parameter which is taking some space. Okay. So this is a phase diagram we obtained. So indeed we had all the 4 phases. Okay, we have all 4 phases. And this phase diagram is obtained by this tensor network calculation. So actually this tensor network calculation is quite good, we can get a very sharp transition. And so the effective system size is about maybe at least 1,000 by 1,000 speed, and could be 4,000 by 4,000, so around that neighborhood. Okay, so we get a very good transition, very sharp transition. But from here we see clearly that looks like we have 5 stable continuous transition. All these lines are stable continuous transition up here apparently, except this line. If you look very carefully, actually what this line computes the so-called central charge. Or maybe another way to compute the low energy density states. At the critical point, we have low energy excitation. Then there's a heat capacity. And the heat capacity has this coefficient, in one dimension, the heat capacity is linear in T. And the coefficient of linear T term is central charge. And there's a way to compute this central charge. And then in the gap phase, central charge equal to 0. So it is black. There's no low energy heat capacity, central charge equal to 0. At the critical point, central charge is non-zero. Okay. But and we also other line I feel more confident, because other line you can see has some width. That is crossover regime. That it's not sharp transition. It's a crossover, then to have critical regime, then go back. So we see the scaling regime. So I'm more confident for other 4 is a continuous transition. And also the height of these 2 is a Z2 symmetry breaking transition from S3 to Z3, from Z2 to Z1. these two horizontal line is a Z2 symmetry break transition. It's like icing class. And the other one is a stronger. So this is a Z3 symmetry break transition. It's say from Z3 to Z1. That's a Z3 symmetry break transition, which is actually is a continuous. According to the Ginzburg-Landau theory, this transition allow cubic term actually should be first order, but in reality it's continuous. So I need to explain why Ginzburg-Landau theory predict first order transition, but in reality it's continuous. So one need to explaining that. And this one is mysterious. And we have been from S3 to Z1. The fact that we have this line means looks like it's a continuous transition. On the other hand, this line is very sharp. We don't see the crossover region. Looks like a first order transition. So actually, we are flipping flop to say what is first order or continuous. And one need even a better calculation for this from S3 to Z1 transition. Yes.
So between the Z3 and Z1 and S3 and Z2, it looks like the line is like these dashes with these stripes.
Yeah, this stripe is a artifact.
Okay.
It's my computing. These are pixels I chose. Yeah. And so actually, this if I look very carefully, this graph is have three colors. Each color channel represents different side of the system. So you sometimes can see the scaling when you say the shape like here, you know, the red channel means a smaller system, and then the green channel is even is bigger. Then the blue channel is even bigger. So when right at the transition, all the three side systems have same contribution. It became gray. And so from here you can see this kind of scaling regime. You can see some scaling. Okay. And so this transition is from S3 to Z1 transition is not so clear. Yeah. And then we try to look for literatures. So what is this transition from S3 to Z1? You know, S3 is the simplest non-abelian group. The Ginzburg-Landau theory have been around maybe for, I don't know, 50 years, 70 years. But somehow there's 1,000 papers and I couldn't find one. But maybe I'm not expert in this area, so maybe I didn't look in the right place. But so far I don't know whether any people who study this transition very seriously. Presumably, I think the Monte Carlo can do it. But there's a lot of Monte Carlo result for the Potts model. And so this transition from S3 to Z2 is well known. That's a Potts model transition. But however, to see this S3 to Z1 transition, one need to build this very complicated model with chirality built in. And most model with S3 symmetry don't have this chirality fluctuation built in. So we don't have that transition. So it's kind of surprising that this very simple symmetry for some spin system and this one transition is still kind of unknown. Okay, so this is one thing. Okay, so this is the one possible phase diagram. But if you're changing the parameter, like you're changing this g to be minus 0.5, other j and jc still equal to 1, changing some parameter, then phase diagram changes. Then we have similar one because it's controlled by J1, J2. It's controlled by this icing order parameter and Z3 order parameter. But then again, the numerics, do you believe in numerics or not? And this looks like a multi-critical point. Or you may say there's a small segment of stable Canadian transition separating Z3 and Z2. And I think this is the multi-critical point. And this diagram actually compute the ground state degeneracy. You know, in symmetry breaking, we have a ground state degeneracy. Like for the S3, the ground state degeneracy is 1. So 1 over ground state degeneracy is largest, so that's a white. And for Z1, it has 6-fold degeneracy, is 1 over 6, so it is pretty small. So yeah, so looks like there's a there's multi-critical point. Again, this is plotting central charge, and the multi-critical point is brighter, so have a higher central charge, means a more low energy excitation. All these kind of agree, multi-critical point have a more things. Okay. Then there's again the issue. So what is a conformal field theory describing this multi-critical point? And this vertical one is a Z2 symmetry breaking Ising conformal field theory, and the horizontal one is this Potts model conformal field theory. So they both are known, but this one is unknown. So in this numerical calculation, really say that even for this very, very simple problem, we still have two unknown situation. This what is a multi-critical point? What is the S3 to Z1 transition? Yes.
What is the central charge for this S3 Z1 transition?
Okay. We couldn't pin that down completely, but it's similar to I think 1.3.
Okay.
So it's 0.8 plus 0.5. 0.8 is a possible critical point, and 0.5 is icing. So kind of adding some charge of these two give this one. And but however the standard calculation determines central charge is we don't have very good results. It's a shifting. For different size system, it's a shift slowly, so you couldn't pin that down completely. Yeah. So this is so that's another thing is unknown. So maybe one need to do a bigger calculation. Yeah. And but this is actually this now you can see that we have a real problem here, and then we want to use this kind of sophisticated method to try to answer this question. At the end, we still don't have a complete answer, but at least we gave some opinion on that, So the Kinsman theory actually, I mentioned that it's not very reliable because it even predicts first order transition or continuous transition even at 0 dimension, And so the point really the following, and we need the so-called full quantum theory to understand the critical point. The full quantum theory actually means the fixed point deep IR theory. That's what we try to say. However, the Kinsman theory is not a deep IR theory. It's a mid IR field theory. It's a field theory, but it's not really a low energy fixed point. It's not critical theory. Okay. And but certainly Kinsman theory as a field theory also not the lattice UV theory. Okay. So yeah, actually this line may be representing, after so many years of understanding what is field theory. So the field theory actually is also critical theory, in a sense. If you ignore their interaction, just do free field theory, that's a gapless critical theory. Then this deep IR theory means that we turn on some kind of relevant direction. We flow from one critical theory described by free field to another critical theory, which we don't even have a field. We don't have a weak interacting field. So it's very hard to understand. So this deep IR fixed point theory is very difficult to understand. And so what we did is that from this lattice UV model, we somehow come out with this field theory, which is really not a infrared fixed point. Then you want to go to this deep IR theory, and how to really understand this deep IR theory is what we try to do. Okay. So as I mentioned in my first lecture, so here I'm repeating that. So there's actually here we want to there's a 3 steps to try to move forward to solve this problem. One is we need a theory of a topological order. Why we need that? Well, second, we need a theory for emergent symmetry. So this is the point, because once study gapless states, it's very hard to start. We don't know where to start. So one idea here, we say the gapless theory have a lot of emergent symmetries. We try to collect all the emergent symmetries, and then using emergent symmetry, probably emergent symmetry can fully characterize the gapless states, and you can study gapless states using emergent symmetry. But recently we find that emergent symmetry can be ordinary symmetry, can be anomalous symmetry, can be higher symmetry, non-invertible symmetry, and all kinds of crazy symmetries. So at this stage, we find the topological order is useful because topological order actually is a theory to describing all those symmetries. So this is basically what we try to develop in the previous few lectures. You know, those symmetries are not described by group. The group is not enough. The even higher group is not enough. But however, the topological order in one higher dimension is enough. At least at the moment, we believe that is enough. So therefore, we're using the topological order in one higher dimension to describe all the emergent symmetries. When all the emergent symmetry can be described by topological order, then we can using that emergent symmetry to study the gapless state to see how can we determine the gapless states. Okay. So to really carry through this program, and we need to know that what is the data to describe emergent symmetry? You know, well, as I mentioned, yeah, it's a topological order in one higher dimension. But what is data to describe topological order? So then, you know, we find we have ST matrix, at least in 2+1 dimension, ST matrix can describe topological order. Okay, so that's the first question. The second question, what is data to describe the gapless states with this emergent symmetry? It turns out that the answer for that is the data to describe gapless states, at least the one with the linear dispersion relation, is so-called a multi-component partition function. So there's a partition function with multiple components, and those are data to describe gapless states. And then the third question, how these two data get related, you know. So if you answer all three questions, then we have some kind of theory. Yeah, we can using this emergent symmetry described by topological order to determine the multi-component partition function, which is from where we know what is the gapless theory we have. So that is the idea. So the data to define topological order, to measure topological order, at least theoretically, is like a wave function overlap. Okay. And so we consider we have topological order in 2+1 dimension topological order, and say on the torus. And this topological order ground state wave function there are several wave functions labeled by this alpha. Okay. Then we consider the overlap of two ground state wave function rotated by 90 degrees. So that's from this from xy to y minus x. So that's overlap. Our Hamiltonian don't have rotation symmetry. So therefore, after rotation, the overlap is very tiny. So there's almost no overlap. So overlap is an area of a system divided by some coherence length, something like that. So it's very tiny. But just like this topological entanglement entropy, if you remove the leading term, this area dependent term, the subleading constant term turn out to be universal. And so this is so-called S matrix. So actually S matrix can be computed very quickly by this wave function overlap. And similarly, the T matrix also can compute quickly by doing another shear deformation. XY go to X plus Y, Y. Yeah, this is shear deformation. This shear deformation, again, this two wave function differ by shear deformation, also have very tiny overlap. But again, if you know this area dependent small factor, the constant term independent area is universal, is T matrix. And this ST matrix really is really generating matrix for this 90-degree rotation and the shear deformation. Actually, these two transformations generate so-called SL2Z group. It's called modular group. So these two ST matrix actually representation of this modular group. Okay. So this is the way to extract data which quantitatively describe topological order. Although this ST is not full data, but detail enough actually for simple one. That's all. That's give a complete description. So at the moment we pretend ST is full data and try to build the theory using ST matrix. Okay. And to understand this ST matrix, we also need to understand this degenerate ground state. How to understand different degenerate ground state from quasi-particle picture. And this understanding is necessary because ST matrix, if you do this definition, we say ST matrix only defined up to this choice basis. So under the conjugation unitary matrix, this ST matrix should be equivalent. But actually, no. The ST matrix is not have a special choice of basis. And this special choice basis is related to this understanding of degenerate ground state. So how to understand the degenerate ground state on the torus? So here I draw the space-time picture. So this two sides of a cylinder is identified. So this what I'm drawing here is a solid torus. The surface of solid torus is a current time, which is a torus, so which have a degenerate ground state. Suppose the Hamiltonian in the space-time is a Hamiltonian which is supporting topological order. Okay. And then we have a big bang. So you know this center one is like time equal to infinity, and then evolve into our ground states. Okay. However, for this solid torus, if you evolve this way, you get a particular ground states. So that's one of the degenerate ground state if you're using solid torus to do evolution. Then how to obtain other degenerate ground states? You can do that by inserting anion word line. So this line is a word line for anion. Basically, you create a pair of anion, then wrap around this one direction annihilate. And then at the end, you see nothing, no anion. Okay, but when you create this anion word line, somehow you generate another degenerate ground state. So the point is that the degenerate ground state are labeled by type of anion in the bulk, in the topological order. Yeah. And also in this particular setup, this anion word line give us a basis of a special basis of a degenerate ground state, and this kind of we call the quasi-particle basis. And using this special basis, we can define ST matrix without ambiguity of this choice of basis. So that's basically the point here. Okay. So so this is one thing. Okay. So this is a story about how to use what's the data to describe a topological order. Okay. So the next one is that what is the data to describe a gapless states? Okay. So here, yeah, here the picture is the following. Let me see. Oh, maybe it's on this picture. Here we consider a 2+1D system. So our system is a disk. So this blue one is disk is our system with topological order. Then the boundary of topological order may be gapless. So this is the picture we used before. That's we say topological order describes symmetry. Then the boundary of topological order will be the corresponding system with that symmetry. So this is symmetry and a topological relation. It's really boundary bulk relation. This really describes the boundary with the symmetry correspond to the boundary of a bulk topological order. So that is how things get related. So therefore, we can think about this symmetry is on the boundary we may have a gapless system, a gapless state, and so this gapless state will be a gapless state for the system with this symmetry described by this topological order. Okay, and so the point is that the boundary partition function actually is not number, it's a vector. This sounds very strange because usually partition function just like that. So let me, what's a partition function? Partition function is a trace of e to the beta h. That's a partition function. And we can generalize partition function a little bit to say that instead of no, this is again, this is this part is a beta. Okay, it's just ordered in very strange way. So this L is a system size, and the imaginary part of tau is like a beta. Okay. Then also add this momentum operator. So before we take trace, we also do a translation. Then we take a trace. Okay. So we can get this more general partition function with have a tau dependent partition function. The tau is like generalized beta, but with momentum. So in field theory, this partition function like path integral in this kind of a parallelogram space-time. Yeah, this space-time shape. Okay. And it turns out that the partition function indeed depend on tau. For different tau, you have different partition function. That's naturally. But however, sometimes two different tau only differ by this kind of tau. This parallelogram is the same as a square up to the change of a coordinate. Okay. So that's led to the results that these two partition functions should be the same, because these two tau, although looks like different parallelogram, but they only differ by changing coordinate. So really same shape of space-time. So again, see, this is as well. This is like a 90-degree rotation. Okay. So this we call the modular invariant partition function. Okay. And so therefore that's a usual standard result. The component field theory are described as modular invariant partition function. Okay. But however, for the boundary topological order, the partition function not number. The reason is following. We can insert different quasi-particle in the middle of a disk. You know, we have one partition function if we just have a disk. Then the boundary have a partition function. Then we can create a onion in the middle of a disk. This onion is far away from boundary. We think boundary is not affected. We have another partition function. But however, inserting onion in the center of disk is like changing sector or changing boundary condition will go around the loops. So it's give you another partition function in the different sectors, kind of like. Okay. So then for each onion type, we can get a sector, get another partition function. So the partition function are labeled by this onion type. And for each sector, we get a partition function of tau. So we get this vector-like partition function. So this is another key. It's a vector-like partition function at the boundary topological order. This is true, I think, in any dimension. Then we can answer the question, how the data describing this one-dimensional gapless state, this vector-like partition function, and the data ST matrix describing topological order are related. Then you can almost guess it's a modular covariance. Everything's there, so these things fit together very nicely. It's a modular covariance. Yeah, and so this vector like a partition function is not invariant under modular transformation, but transform in some way under modular transformation. But the ST matrix they transform according to some ST matrix. This ST matrix happen to be the one ST matrix describing the topological order. And in this language, it's easy to see because you can see when you do this modular transformation to do this to change the partition function, it's kind of like it's kind of like this is really like this this waveform overlap. This is also modular transformation. The difference that you can see the picture is very almost same. Here the radial direction, time direction, and the surface is x, y. We just changing the coordinate. Now the time direction became this surface time direction, the radial direction, the y. It's just changing t and the y. Changing some coordinate. The whole picture is the same. And so actually this kind of cartoon picture kind of convinced me that yeah, we have this result. And these are the key results. That is this partition function and the topological order and symmetry are related this way. Okay. And the difference is that we emphasize that this ST actually describing emergent symmetry. This ST image describes emergent symmetry. And this result tell us how emergent symmetry determine the gapless states. So that is a concrete result. So how emergent symmetry determine gapless state. And one may say this result is very weak because we want to determine a function, the partition function, the function of tau. We only have two algebraic equations. So it's only finite algebraic equation. The finite algebraic equation cannot determine a function. We don't have enough equation. We have too many unknowns. So this is a problem. But however, because of some kind of number theoretical consideration, this algebraic equation probably is enough to determine this function. Yeah, the reason is a kind of have some number theory flavor. Okay. So we just look at this. Partition function more carefully. This we can diagonalize Hamiltonian and the momentum, so it has some eigenvalues. Then for each eigenvalue, there's some contribution. So that's the partition function. Okay. It turns out that for each eigenvalue, the contribution is this Q. The Q is this combination of e to the 2 pi I tau, which roughly is a beta E and plus is a momentum shift. So something like that. So therefore, for each eigenstate, there's contribution of Q. So therefore, this partition function is a polynomial of Q. Okay. Yeah, I should say that this what I say is not quite accurate. It's that this Q just e to the I tau is correspond to the state with the momentum maybe 1 over L. Okay. Or with energy 1 over L. In conformal field theory, we have linear dispersion relation. The old energy level is multiple 1 over L. So it's n times 1 over L. So for that energy level, the contribution would be Q to the nth power. Okay. Yes.
You're assuming non-chiral?
Yes, this is non-chiral. Yeah. So it's a little bit tricky, but anyway, so at least for conformal field theory, all the examples we know, and this partition has the following thing. There's some fractional power here due to some boundary condition. So let's ignore this fractional power. And after removing out the fractional power Q, the all other power Q are integer. Means the level spacing just 1 over L. Maybe there's an overall shift, level spacing 1 over L. Then for all these levels and the contributions of Q to some power. From here, what I try to get at that is the coefficient of Q to the nth power, and the Q bar is Q for right mover, Q bar for left mover. Again, there are two movers, so there's in one dimension the left mover, right mover is a Q and a Q bar, and the coefficient of this Q to the nth power, Q bar to the nth power, actually is a degeneracy of that energy level. Yeah, so that is a basic understanding. So this polynomial is just not arbitrary polynomial of tau or polynomial Q. It's a polynomial with an interpretation that the coefficient, expansion coefficient, is a degeneracy of that particular energy level. So therefore, the expansion coefficient is non-negative integer. This is a very important condition. And so therefore, this is an amazing function. It's a polynomial of a non-negative integer expansion coefficient. And the claim is that for this special polynomial, and this equation may have a discrete solution. Yeah, may not determine that completely, but maybe largely determine what function is, maybe up to some discrete choice, discrete ambiguity. Okay. I think this is the key of this a new way to solve a quantum critical point. Yes, but this the essence of this approach really is a number theoretical approach. Yeah. So this approach actually is very similar to so-called modular bootstrap. The modular bootstrap is doing the same thing, but for modular invariant partition function. Yeah, that's a modular bootstrap. So we can generalize it slightly, because generalized modular bootstrap, we just do this modular covariant multi-component partition function. It's a slight generalization. Okay. And you may heard about this all this bootstrap or conformal bootstrap thing. My understanding is the following. At the moment, we don't know how to use this non-negative integer condition. So people don't know how to do that. So I think the conformal bootstrap or modular bootstrap, people only use the non-negative condition. Ignore the integer. We find this polynomial with the expansion coefficient non-negative. Then to see, can we find a solution or something? You may say, oh, this integer is so important. You say, just say non-negative is you lose too much. But we know that this modular bootstrap with only non-negative condition already became very hot field. So if you add integer condition, it became even hotter. I don't know, but it's too hard. So nobody can do anything at the moment. Yeah, but this I just want to emphasize that yeah, it is a huge desire to do this problem. Yeah, it will be bigger progress than the modular bootstrap. That's than the conformal bootstrap. Yeah, so try to putting this integer condition into the game. How to do that? Okay. And so at the moment, we don't know how to solve this problem. So this is a nice program, but we don't know how to do it. And but there's a hacker's way to do this. And in one Poisson dimension, we have a library for so-called conformal character. And so for each chiral CFT, we have some partition function or some character, and they transform like that. And this conformal character is a set of those conditions. They have this form. It's they're polynomial with a non-negative integer coefficient. So you have a library for that. Okay. And then so the guessing is that then using this using library of conformal character, we just pick a two, one for right mover, another for left mover, then put them together, and using some kind of a Calabash-Gordon coefficient, some kind of coefficient of combine two repetitions together. You know, each conformal character is a repetition of SL2Z. When you have a two repetition, you get tensor product of two SL2Z repetition. Then you need to do projection, project into some proper SL2 repetition, which you desired, what you desired for this topological order in the bulk. But if you pick these two conformal characters randomly, you find there's no solution. There's no projection for the no projection to what you want. Now you need some intuition to pick a proper one and plug in the program to check it works or not. If that does not work, pick another one. And for simple one, we can usually make an educated guess and to find it. So at the moment, this is we got this kind of approach. Certainly is not desirable, but that's what you can do. Hopefully, we have a more direct way to handle this. Okay. So so this basically is the program. Yeah. So any question here? Yeah. That's how we going to handle this problem. Yes.
So this is to get not the so you can make CFT1, CFT2 do the same thing, and then that gives you the usual non-character.
Yeah.
But you want to build something more non-trivial.
Yeah. Sometimes it's a CFT1, CFT2 can be different. You know, right mover, left mover can be different, especially for anomalous symmetry. For anomaly free symmetry, than the same. But usually anomaly cocycle break time versus symmetry. So the right mover, left mover can be different. Yeah.
Are you assuming that you know the fusion algebras of these individual symmetries?
No, we don't. So this is a nice thing. We only need to know their SL2Z transformation ST matrix. So those are programs built upon this modular transformation. There are more data, more structure like F symbol, this algebra, this operator product expansion coefficient, all this structure, and so that makes things very difficult. Actually, conformal bootstrap using this operator product expansion. But I feel that this modular bootstrap are easier. We don't need to worry about that. And also it's also very effective, you know. Another thing, we hope this setup actually work in any dimension, supposed to work in any dimension. We hope to work in any dimension. But again, we need a non-trivial example to really check it. We could be wrong in some place. And I hope it is not wrong, because the whole thing is so reasonable. And from 1+1 system as a boundary, 2+1 system is just an example. And the generalization to higher dimensions seems pretty straightforward, the way we set it up. Yeah. Okay, so let's just do this calculation now. But as warm up, we'll do the gapped state first, then we do gapless. So actually, this approach not only works for gapless boundary, also works for gapped boundary. Okay. Then for gapped boundary, what happens is that the conformal character is just equal to 1. You know, when a boundary have a gap, it's trivial. It's just a one state, just ground state. So conformal character is equal to 1. And the label, we don't have an R sector, we just have one state. So the alpha just one index is 1. Okay. And then the partition functions do not have a tau dependence. That's also natural, because when you have energy gap, the tau is like space-time metric. You don't see the metric, it's topological. So no tau dependent. This partition function is a constant. Okay. And so therefore, this partition function just became this n11, you know, the alpha bar just equal to 1. So this kind of disappears. So the partition function just ni. And so we call ni just ai for another reason. So it's just a vector. But ai is because again, this is a polynomial of non-negative coefficient. This polynomial just only have constant term, don't have other terms. But this constant term is ai has to be integer. It's actually described degenerate ground state. That means on the boundary also have energy gap. There may be ground state degeneracy. So actually, this ni or ai just describe ground state degeneracy. So therefore, this ai or ni or zi, they're all same thing. Just they're really describing the degenerate ground states on each sectors. The sector means I insert a quasipart in the bulk. Then we say whether boundary have a degeneracy or not. Okay. And sometimes this ai can be 0. Okay. So it means zi can be 0. Partition function to be 0. 0 really means that when you're inserting quasi-particle in the middle, these quasi-particles do not disappear at the boundary, because we can never create a single onion. We always create a pair of onion. Then one stay in the middle, another shift to the boundary. Hope this onion is absorbed the boundary, means condensed on the boundary. Then disappear, become ground state. But sometimes this boundary cannot absorb this onion, so the onion remain there on the boundary. Then this onion have a finite excitation energy gap. Then our partition function are really done in the thermodynamic limit. So when you have something with energy gap, the contribution with the e to the minus e times the beta go to infinity. So this e to the minus e beta becomes 0. So this is physical interpretation that when the partition function is equal to 0, that means we have uncondensed onion on the boundary, which cannot. I mean, the onion creating the bulk cannot condense on the boundary, basically. It really means that. Okay. However, if partition function is non-zero, means that that corresponding anyang will be this condensing on the boundary. Then from this result, we see that if we have non-anyang, the partition function z1 should be equal to 1. It's always equal to 1. So that's a trivial sector. Okay. So so this is so this is the picture. Okay. And so how to describe this this partition how to compute this partition function or this AI? How to compute this AI? Okay. Well, I just mentioned that well, the AI should satisfy this condition. Yeah, that's it. It's modular covariant. Okay. And also remember, A1 should be equal to 1. That means in the trivial sector, the ground is non-degenerate. And other sector, it depends on what you have. You may get the other solutions. Yeah. Okay. And so there's other things. Let me just jump ahead a little bit. Okay, so let's get some example to see what happens. So let's consider a simple Z2 symmetry. Remember, Z2 symmetry in 1+1 dimension is described by Z2 gate theory in 2+1 dimension, or Z2 Tor code in 2+1 dimension. So for that Tor code topological order, that's ST matrix labeled by this T and S matrix. That's the ST matrix. Okay. So so there are several things I want to mention that. First, the T matrix, the diagonal part of T matrix representing the self statistics of anyons. Like this one, trivial particle is a boson. This E particle is a boson. M particle is a boson. This is the F. -1 means F is a fermion. And S matrix for the abelian topology order, which is Tor code is abelian topology order, have an interpretation of a mutual statistics. Okay. So this alpha diagonal element describe mutual statistics. So that means E and M have a pi mutual statistics. And also E and F have a pi mutual statistics. Same thing, M and F have mutual statistics. So you have this kind of interpretation of a T and S matrix describing their statistics and mutual statistics. And then we can solve this condition. You solve this condition. We find these two solutions. Only these two solutions. Certainly, there's more solution. You can scale this solution by an integer value, get another solution. But that solution have an interpretation of accidental degeneracy. We can have accidental degenerate ground state. So if you remove this accidental degeneracy, the minimal solution, or maybe it will require this A1 equal to 1. So that's with no accidental degeneracy, that's the minimal solution. The first solution, remember this AE equal to 1. So this second component is anyang E, A equal to 1. That means E anyang can be absorbed at the boundary. So there's E condensation. Okay. Then the third component is M, so that's the M condensation. And luckily, if you solve this, that's only two solutions. We don't get the 1, 0, 0, 1. If you get that solution, that means F would condense on the boundary, but F is a fermion and cannot condense. So naturally, such thing is not there. So this is a simple equation, and just give something very reasonable. Yeah, and this two boundary is exactly the two boundary we have. You know, when M condense on the boundary, that's correct. Z2 symmetric states. If E condense, that's a Z2 charge condense. That's a Z2 symmetry breaking states. Yeah. And no other solution means Z2 have no SPD states. Indeed, Z2 symmetry have no SPD states. So there's no other solution. Okay. And so to describe condensation, and we'll put this solution into this 1 plus E form. This really means that one can condense, E can condense. And then this composite anion, so this 1 plus E is a composite anion. This composite anion can condense. So this way of describing condensation is a more appropriate, because sometimes you may have a solution 1 and 2, 0, 0 could be a solution. Then the condensing anion should be 1 plus 2E. So in a simple language, we don't see what's different between 1 and 2, but actually in the mathematics, the 1 and 2 make difference. Yeah. So because this, so this is the better way, using this composite anion is a better way to describe pattern for condensation. And this is called a better way to describe pattern condensation is called a condensable algebra. So this condensable, this is a one anion plus another anion is a condensable algebra. Okay, so let me explain this a little bit more. What is algebra? Algebra means that you have a vector space. In the vector space, you have a vector. The vector can naturally add. Okay, but the vector also can also multiply. So that's the algebra. So why you call this a 1 plus E a condensable algebra? In a sense, well, 1 plus E actually describes a vector space. 1 is the basis of one vector space. E is another base of vector space. Actually, you remember this in general 1 and E, those anion may have a non-zero quantity dimension. So each anion may correspond to a vector space which may not be one-dimensional, maybe even non-zero dimension. So so this 1 plus E really describing this vector space. So then you say you should not call 1 plus E a condensed algebra. Indeed, I should not call that because it's just describing vector space. I did not give you the algebra. So in the mathematical theory for condensed algebra, not only you have 1 plus E, we also have another data describing how those vectors inside the vectors multiply. And that is called condensed algebra. But it's just like F symbol. Those structure constants of algebra is very complicated. And apparently at some simple level, we can ignore that. Just like we use ST matrix to describe topological order, ignoring F symbol. F symbol is very important data. Ignoring that is bad. But looks like if you ignoring that, just do SNT matrix, you more or less get some kind of self-contained theory to some degree. And so we are doing similar thing here. We only describing vector space of the condensed algebra without even talking about algebra. And this looks like, in many cases, this is enough for us to get some results. So I'm describing a simplified theory, not the full theory. That's what I'm trying to say. So so therefore, again, so now we can see this condensation. So there's another picture which is important. That is here we're describing this condensation as the way to get the gap the boundary. Yeah, sure.
So calculate this AI, we are calculating the partition function with some boundary and inserting an anion.
Yes.
What if I consider like a mixed boundary, rough on one side, smooth on one side? Is that important?
Yes, that's possible. Yeah, that boundary have a domain wall, boundary domain walls, and so I did not consider this situation. Basically, the boundary we considered here, we just all have a same condensation from box to boundary. So describing a same condensed algebra. It's possible that maybe on the left half, you get one condensed algebra condensation boundary. Another half, you get another condensed algebra. You know, different condensed algebra just give you different gap the boundary. And so therefore therefore by calculating condensed algebra, you're actually calculating gap the boundary. So that's another way to classify the 1 plus 1 dimensional gap the phase. That would include SPD space. You can have that, yeah, but we're not talking about that, yeah. And but however, the picture I'm describing here is that we are using condensed algebra to construct a gap the boundary. But what we really have is that those kind of anion in the condensed algebra, because these two conditions, you can see this condition means that the the anion in condensed algebra should be boson, because this condition means the A should be the eigenvector with eigenvalue 1. So it can only be boson. And this condition basically say that the different anion in the same condensed algebra should have trivial mutual statistics. Yeah. And yeah, there's some condition like that. Okay. And so basically, the anion in the condensed algebra is a boson with the trivial mutual statistics, and they can condense together. Okay. And when they in the bulk phase, when they do condense, and also if this condensed algebra is a maximum, we can have all the anions with the trivial mutual statistics with the boson, all them together. They will destroy the topological order completely. So this is a maximum condensed algebra called the Lagrangian condensed algebra. This maximum one is called the Lagrangian condensed algebra. And then if you're condensing this maximum set condensed algebra, we destroy topology completely. Then we get then the boundary of this trivial topology order with my original topology correspond to gap boundary. So this is one way to understand this condensation and the gap boundary. So the so the picture is that if you're condensing maximum set, we get the gap boundary. Okay. And however, there are also other condensed algebra which is not maximum. So it's a subset of an anion with a trivial mutual statistics, but not the maximum set. And so how to determine this non-maximum set? Okay. And so the let me try to see the okay. To determine this non-maximum set is tricky, because if it's non-maximum set, we cannot use this this condition. This condition is we cannot use that. This condition only apply for the maximum set. Partial A, if only do not satisfy this condition. But however, there's other way to determine the non-maximum set. And so I will not explain it. I don't know how to derive them. But basically, I say that this condensed algebra or basically this AI satisfy this condition that each AI should be a non-negative integer, and the component labeled by anion type. I is just a different anion type. Is non-negative integer, and A1 equal to 1, so means the ground state should be equal to 1 for the trivial sector. And for the anion and the conjugation of anion, these two A should be the same. Okay. And also this if A no, I didn't say this okay, yeah. This I say that in the lesson. So if AI is non-zero, so I belong to A means if AI equal to non-zero, if AI is non-zero means that anion is there, then the corresponding T matrix has to be 1, means it has to be boson. So therefore, this condensed algebra are formed by bosons. So that's condition. And those conditions is harder to appreciate. And but it's really some categorical theory. So basically, you have S matrix, you multiply AI, and S matrix 1. This particular another S matrix times AI. So the ratio of these two numbers, just general complex number, they should be so-called a cyclotomic integer. Means the cyclotomic number means it's a root of unit with a rational coefficient, some combination of root unit with rational coefficient. The cyclotomic integer means the combination of root unit with the integer coefficient. So it have this kind of property. And then there's some other properties, So basically, there's a way to determine this using this. Actually, there's a review paper here by Liang Peng, which is discussing this. And yeah, that paper is it's not so easy to read, but that's already a translation from mathematical paper to physical paper. And so what I did here is a further translation from mathematical physics paper to maybe condensed matter physics language. Yeah. And then this is those are really a necessary condition for condensed algebra, and it's pretty good, but it's not sufficient. I mean, so therefore, when you find this AI satisfy those conditions, some of them can be fake. Yeah, and but this is still open question. Yes.
So supposedly, if it's not like a maximal condensable set, then you still have some gapless mode. Then we should go back to the partition function.
Yeah.
Right. It's not just number.
Exactly. So this is that's why I go through this. So so if you have a maximum set, maximum certain those conditions also allow you to obtain a maximum set, or those Lagrangian one. If you do that, you basically obtain a gapped boundary. So this calculation almost like trying to classify gapped phase with an arbitrary symmetry. Yeah. So even for non-invertible symmetry, you can do the same thing. And but unfortunately, this formula is condition given is not necessary and sufficient. So therefore, you may get some fake results. But imagine you can get the full results. Then that's basically is a classification of SPD states, even for non-invertible symmetry, or for any symmetry, anomalous or whatever. It's all here. That's thing. And then as you mentioned that if you find the condensed algebra which is not a maximum, then you also have then we believe that's became a belief. We believe that we also have a boundary, but that boundary cannot be gapped, must be gapless. Okay. And the picture actually is this picture. Suppose we have A which is not maximum. So then we can condensing those onions in M. After condensing that, you get M/A. And this topology is non-trivial because it's not maximum. Actually, that's definition of maximum. After condensing those onions, you still get non-trivial topology order. And then we have this no condensation boundary of this M/A. Means that because we already have A condensing here. We don't want additional condensation. So therefore, on this boundary, we have one condensed boundary. The trivial only, nothing else condensed. Then this combination of boundary is like a condensed boundary for the M topology order. Okay. And so from here, maybe we'll start from here next week. That the one condensed boundary of a non-trivial topology order is always gapless. Yeah. So this is a way to understand this symmetry protect gaplessness. If a categorical symmetry is non-trivial, then this one condensed boundary, if no symmetry breaking, always give you a gapless boundary. Yeah. So one way to understand the A condensed boundary is to compute this topology order of A condensation induced topology order, and study the one condensed boundary of this M/A topology order. That gives you this A condensed boundary. So therefore, this gives you the general picture. This maximum condensed algebra or Lagrangian condensed algebra give you a gapped boundary, classify gapped phase. Then we hope non-maximum one gave rise to gapless boundary, and so we have an understanding of a gapless phase. But there's one thing I want to say that, strictly speaking, the maximum condensed algebra do not classify gap phase because of the. Okay, there's some redundancy because you can see if you multiply this solution by 2, that's also a solution. But we say this if this 2200 is not a stable solution, have external degeneracy. So therefore, when we say the condensed algebra classify gap phase, we have an assumption the boundary is minimal. There's a minimal in some sense. We don't have external degeneracy, and this feature also shows up in the gapless boundary. There's actually more than one solution, and we need one minimal one, things like that. But anyway, yeah, this is basically give you some kind of a picture. So what's going on? So how to use the emergent symmetry to determine a gapped phase. And so the next week we'll do this for gapless phase. Yeah, so that's maybe a way to apply this. Okay, got questions?
Yeah, so I was wondering, this regeneracy, the different boundaries you have. I was wondering if there's a microscopic way to think of it. With like, so for instance, by the Burke code, like the rough boundaries is the E and boundary,
Yeah.
the smooth and F-10. But then there's also like the one fence boundary, which is like this staircase looking boundary. How can I, like, is there a picture from this lattice where I have a staircase bound, the staircase
Yeah.
boundary, that there's could be multiple different like gapless modes?
Yeah, the point is that this yeah, I don't quite understand your question. So basically we try to say that the condensation determines boundary, but I don't cannot say more or less. I cannot say completely determine the boundary, because you can always stack with another gapless system to the boundary, and that's give you another boundary. But when you're stacking another gapless system, that means it's not minimal, so it's extra. So you need to find the minimal one. So we hope that once you specify what condense on the boundary, if the condensation on the boundary is not maximum condensed algebra, and then you ask what is the minimal gapless boundary, maybe there's a few unique solution. Yeah. However, for the concrete system, how to obtain this gapless boundary is a very big question and a very important question. Because for the gapless boundary, we seem to have a program. We have a commuting projector model realized about topological order. We can have commuting projector boundary Hamiltonian realizing all the gapless boundary. But we don't have a similar story for gapless boundary. We really wish we have. And now we feel we are ready to attack this question because we know what we want. Because this gapless boundary is characterized by a non-maximum condensed algebra. So hopefully there should be design based on this non-maximum condensed algebra. We can design the boundary Hamiltonian which realize this particular boundary gapless phase. But the gapless boundary is not commuting Hamiltonian, so that's immediately make it much harder. So at the moment, I think we see missing something essential to really do this, to construct the boundary Hamiltonian which realize this. For the staircase boundary, so there we have a trick. There's EM exchange symmetry. So you try to construct the boundary with the EM exchange symmetry. So maybe that's another way to say that. Let's don't construct the gapless boundary. We try to construct a boundary Hamiltonian which respect certain symmetry in the bulk topological order. In the bulk topological order, sometimes have some symmetry, and respecting those symmetry, maybe that's one way to construct a gapless boundary. So indeed, constructing gapless boundary is a big question. And if you know how to do that systematically, that's also help us to construct those gapless states systematically and classify them systematically. So that is a hope.
So just so I understand, like if I ask my system model, I find a gapless boundary, it may not be the minimal gapless boundary. I may have to like,
may not be minimal exactly. Yeah. Hopefully we can address that issue. I don't know next week I can finish, but there's a maximum categorical symmetry. You know, when the gapless boundary is not minimal, you really have a more emergent symmetries. So actually you should expand the bulk topology, make a bigger bulk topology order, so that to realize to discover more emergent symmetry to realize that gapless boundary. Yeah, this is very important. Usually when you stack another gapless boundary to a gapless system to a boundary, the gapless system carries its own emergent symmetry, but you did not look at it. Then you should view this gapless system as a boundary of another topological order and also changing about topological order as well. Means you uncover the emergent symmetry. Yeah. So basically, in field theory language, you want to uncover all the topological defect line. Then that may determine the gapless theory. Yeah. Okay, thank you. Yeah, see you next week then.